Welcome back. We're going to actually look at pointers and this constant notation that we have discovered in the recent past and see how this actually operates. So first, what this is about. If you remember, the const keyword is meant to make an entity read-only so that you cannot accidentally modify it. It's extremely convenient and it can be used with any types, meaning you can use it on an integer, a character, a string, whatever you like. So it works on objects, but it also works on pointers, and that's where it gets a little interesting. They provide a way, our pointers, to reach an entity. It's kind of an alias. You provide a different name, and you can use that name to read and write. And that's the important part. That alias can be used to write. So if you have an entity that's constant, you shouldn't be able to write to it. And const pointers actually provide us with that ability. So const, it extends to the pointer world. It adds a little bit of complexity though, because you really have two entities that you're contending with. There is the pointer and the thingy being pointed to. And the question, of course, is, well, what is constant? And the answer is one, the other, or both. It's completely up to you to decide what's constant. So we're going to look at an example and see how we write down the types to actually make this work. So let me pop up first in the Emacs window an example of a program, and here it is. This is a fairly straightforward program, right, as you would expect. We include IOStream at the beginning. We have our main function. We're using the namespace std, and we define an integer, which is x. That integer is not constant, right? It's just an integer. It can be overwritten. But then I do something funny. I have this px, and it's a const int star. And it's equal to the address of x. So that's how I initialize it. So if you recall from last time, the mental model that we should be working with is that we have our stack. We have a pointer to the frame. We have some management data in the frame. This is the frame of the function main. And here we have x, right? And x currently has value 10. And we can actually write to that thing. Now, what we've added is that px, which is here, it's the next variable, px, its value is none other than a pointer to the beginning of the memory zone containing our x. So far, so good. There are absolutely no difference with this, right? When I ask for the address of x, I got this arrow, and then I stored it. So there are no differences whatsoever. The difference that appears is in the nature of the pointer we have defined. It's a constant pointer. And what that basically means is the following. The way we read this is that we read it backward, in a sense, in this simple case. Px is a pointer to an integer that happens to be constant. So I'm reading the types backward. So really what we're saying is that this block of memory cannot be written to through the pointer px. You cannot make a modification. And if I have the next two lines that basically print the pointer and the value pointed by, and then if I try to write to px, what should happen? Well, if it's a constant pointer, or a pointer to a constant in, I should say, then you guessed it, this should be flagged as a compilation error. So let's just check this quickly and fire up a shell. And now we're going to go C++ pconst1 minus o pconst minus std c ++14, hit return, and there you go. It tells us immediately, error, read-only variable is not assignable. And it points you to the assignment of 20 to the variable star px, that is, to whatever px is pointing to. And he's telling you, like, no, you can't, sorry. You told me that this was a pointer to a constant integer, so therefore you can't use it to write to that location. Note, however, that if I go back, there is nothing here that prevents me to actually not do that, but write to x, right? This should be okay. And we'll verify that this is working. And I'm going to actually read using the constant pointer. So I will have two outputs this time, one before the assignment and one after. And since here I'm accessing x, which is not declared to be constant, this should be perfectly okay. So let's give that a shot. I go to the other window, I compile, no compilation error, and I run pconst, and you get exactly what you were expecting. You notice as well that while, of course, the pointer hasn't changed, if I change the content of x through its initial name, then the change was allowed. And when I look it up, when I read using the pointer, it's all okay. Now, of course, if I tried to write using the pointer, that still wouldn't be fine. So this is a fairly simple setup in this case to get this working. So let's go back to the empty buffer and to our slides. Okay, good. So that's the program we've looked at, right? The big lesson here is that you're reading this type backward. Px is a pointer to an integer that happens to be constant, okay? And we're going to refine that rule. I'm saying that we're reading the type backward, but there are multiple ways to look at this, so we'll refine this way of reading types. Now, here is a slightly different program. Notice that between the two, the only thing that I've truly done is take this const that was here on the edge, and I moved it on the other side, right? So that's what it looks like. I have an integer pointer const px. So now, how does that read if I read it backward? Px is a constant pointer to an int. So what is constant in this case is not so much the value, it is the pointer. I cannot change that row. And notice that when I make the assignment to px at the time of the declaration. I can assign px only once. Once this is done, then the value of the pointer cannot change. The pointer is constant. So now, if I say I print px and I print what is pointed by px, everything is okay. If I write to px the value 20, well, since x is not claimed to be constant, that should be authorized. I can write to that memory cell. I haven't said that through the pointer it was constant, so that's okay. But the next one that increases the pointer px by 1, which would do what? Well, think about it. It would basically move the pointer, rather than pointing here, it would be pointing up here, right? Into that memory zone. And that is not going to be allowed because it's changing the pointer, and we've said that the pointer should be constant. So let's just check in the compiler and make sure that this is the case. So I'm coming back down here, and I'm going to load, you guessed it, I have a second test, pconst2, so that's exactly our scenario. Right now, I have int x, int star px. Oh, it's not constant yet, so let's edit the program to reflect this. What I'm really doing, right, we see it above, is int star const px. Then I set px at 20, and I increase px by 1. If I do that, what's happening? Let's save. Let's go, into the shell. And we're going to compile. Now it's pconst2. And of course, he complains on this assignment, telling me like, well, no, it's not assignable. You cannot modify the pointer. The pointer is claimed to be constant. You cannot override it. We have an error. Note, of course, that if I change this and I go right back to what I had a second ago by removing this const, save, go back, compile. Now there are no const anywhere. So the pointer is not constant, and clearly at that point, if I run the code, yes, it works, and he allows me to increase the pointer. I'm not printing the pointer after we could do it. Look at what the value of the pointer here is, 9b8, right? So let's see what happens when I rerun this, and I'm going to reprint the pointer after it gets increased. Switch again, compile, run, and yes, that's exactly what we guessed would happen, right? D9A8, and then it becomes D9AC. So indeed, what happened is my pointer got increased. That was A8 in hexadecimal, and it jumps to AC, which is indeed 4 bytes higher in hexadecimal. So we get exactly the behavior we were expecting. We can override the pointer when we don't use the const annotation. We want to protect against that. We just use the const here, and then the compiler won't let you change the pointer px. Now, you're probably thinking, hey, but what if I want both the pointer to be constant and the value to be constant? Well, you guessed it, these const annotation combine. So I can come over here and simply say, oh yes, that's my type. Now, this looks a little harder to read, but it's still the same story. Px here is a constant pointer to an integer that happens to be constant. We've read it backward, and we picked up all the types describing what px is. That's all there is to it. This is perfectly okay. Now you would complain both on this statement and on that statement, because I cannot change what is pointed to by px, because the value is constant, and I cannot change px itself because the pointer is constant. That's a simple idea, and you can work with that with no difficulty whatsoever. Good. So next time, we're going to actually talk about something really interesting, which are known as spirals. And as you noticed, what I've done here is read my type backward, but the types can get more complicated, and we need to have a better way to do that. So we'll do that next time. See you next time.